Design and analysis of heavy-duty truck brake drum and shoe. Abstract: the effect of materials on the brake performance of heavy-duty truck is studied using analysis software. The drum and shoe model of heavy-duty truck were designed by CATIA software, and by using various brake materials as a design variables, the structural and thermal analysis of the imported model was done on ANSYS software. Finite element method was utilized, and the meshing element size and shape were defined to find solution for stress, strain, deformation, temperature, and heat flux of the brake drum and shoe. The result of analysis showed that by assigning different materials, better brake performance can be achieved. Aluminum metal matrix composite F3D205T5, one of the 4 assigned brake materials, has better characteristics of thermal dissipation and lightweight than cast iron and carbon steel, and it has moderate deformation characteristics similar to cast iron. Because of its observed better characteristics, aluminum metal matrix composite F3D205T5 can be treated as an alternative brake material for brake drum and shoe. Keywords: brake drum, brake shoe, structural analysis, thermal analysis. 1. Introduction. Brake is a safety device installed in a motor vehicle to control the movement of the vehicle. It decelerates the speed of the vehicle or stops the vehicle. 1. Based on the type of construction, motor vehicle brake can be classified into disc brake and drum brake. The drum brake is consisted of brake drum, brake shoe, pad, and wheel cylinders or brake chambers. For pneumatic brake, the brake force exerted by the driver on the brake pedal is transformed into brake pressure of brake shoe or pad, and this pressure is distributed throughout the circumference of the brake drum to decelerate the velocity of the vehicle. The friction between the expanded brake shoe and the rotating brake drum generates heat, and the generated heat is absorbed by brake fluid, mechanical parts, and surrounding atmosphere. To prepare the brake drum for continuous brake application, the absorbed heat might be removed from the brake system rapidly. The performance of brake to control the motion of a vehicle depends upon many factors. The mechanics of the braking process suggest that there are at least 5 distinct facets of braking performance deserving of considerations for passengers' car and commercial vehicles. These facets or measures of braking performance may be referred to as effectiveness, efficiency, response time, controllability, and thermal effectiveness too. To operate properly, the brake system should have the following requirements. The brakes must be strong enough to stop the vehicle within a minimum distance in an emergency. The driver must have proper control over the vehicle during braking, and vehicle must not skid. The brakes must have well anti-fade characteristics widely used than any other brake design, i.e. their effectiveness should not decrease with constant prolonged application. The brakes should have well anti-wear properties. The important requirements of the brake drum are following. It should provide a surface having well anti-wear qualities. It should allow the optimum rate of heat transfer. Heat is generated during each brake application, and it must be dissipated to the atmosphere immediately, because the next brake application would again produce more heat. Any excess heating of brakes would cause the drum to expand, resulting in loss of effective pedal travel and fading of brake lining. It should have sufficient strength but minimum weight. It should be able to be accommodated within the wheel space available. The design and analysis of brake requires software that has designing and analyzing tools. CATIA and ANSYS are some of commercially available engineering software which has many design and analyses tools. They enable to build solid models, analyze and simulate the fitness of the model by applying various loads. To design, they usually uses CAD tool, and for analysis they have a solver that have a finite element method tool. ANSYS software is used to design products and semiconductors, as well as to create simulations that test a product's durability, temperature distribution, fluid movements, and electromagnetic properties. 3. ANSYS, like many other FE programs, is also divided into 3 main parts: processors, which are called preprocessor, solution processor, and post-processor. Preprocessor. To do this, FEA software typically uses a CAD representation of the physical model and breaks it down into small pieces called finite elements. This process is called meshing. The higher the quality of the mesh collection of elements, the better the mathematical representation of the physical model. The primary purpose of an element is to connect nodes with predictable mathematical equations based on stiffness between nodes. The type of element used often depends upon the problem to be solved. Each element is comprised of two or more nodes which help define its shape as well as to convey physical reactions from one element to the next. The finite in phi comes from the fact that there are a known number of elements in a finite element model. The solver adds up the individual behaviors of each element to predict the behavior of the entire physical system. Other aspects of the pre-processing phase involve identifying material properties and environmental conditions the design will be subject to. These conditions include various forms of physical forces, loads, pressures, moments, etc., thermal loads and conditions, temperature, conductivity, convection, etc., and constraints, fixed, pinned, frictionless/symmetrical, etc. Solver. ANSYS workbench employs 3 of the ANSYS solvers and automatically chooses the most appropriate or efficient solver for the job at hand. In addition to linear/static, ANSYS workbench performs coupled analysis types, thermal stress, stress modal, thermal stressidal, as well as some limited nonlinear analysis types, thermal with temperature-dependent material properties and convection, geometric/contact with contact supporting liftoff. All solver settings and iteration propagations from one solve step to the next are performed automatically. Post-processing is used to create graphical displays that show the distribution of stresses, strains, deformations, temperatures, and other aspects of the model. Interpretation of these post-processed results is the key to identifying areas of potential concern, weak areas in a model, areas of material waste, areas of the model bearing little or no load, or valuable information on other model performance characteristics, thermal, modal, that otherwise would not be known until a physical model were built and tested prototype for. This study is focused on the design and analysis of trucks' brake drum and shoe to observe the effect of engineering materials on the brake performance of heavy-duty truck. The model is designed by using CATIA v5 software. ANSYS has been used to analyze the structural and thermal properties of the built model. 1.1 Background of the study. Brake is a control mechanism mounted on vehicle to control the speed of the vehicle by applying brake pressure at the road wheel. Depending on the type of operation, brake can be classified into hydraulic, pneumatic, hydropneumatic, and electric. In the case of pneumatic brake, commonly used on trucks, the pedal force applied by the driver on the brake pedal opens the brake valve to allow compressed air to pass into the brake chamber and turns the camshaft to actuate the brake shoe/pad against the rotating drum. Due to the applied brake pressure, the kinetic energy of the vehicle is converted into heat energy at the road wheel. The energy absorbed by a brake depends upon the type of motion of the moving body. The motion of a body may be either pure translation or pure rotation or a combination of both translation and rotation. The energy corresponding to these motions is said to be kinetic energy. The energy absorbed by the brake and transformed into heat must be dissipated to the surrounding air in order to avoid excessive temperature rise of the brake lining. The temperature rise depends upon the mass of the brake drum, the braking time and the heat dissipation capacity of the brake. The highest permissible temperatures recommended for different brake lining materials are given as, for leather, fiber and wood facing from 65 to 70 degrees Celsius, for asbestos and metal surfaces that are slightly lubricated from 90 to 105 degrees Celsius, for automobile brakes with asbestos block lining from 180 to 225 degrees Celsius 5. Since the energy absorbed, or heat generated, and the rate of wear of the brake lining at a particular speed are dependent on the normal pressure between the braking surfaces, therefore it is an important factor in the design of brakes. The permissible normal pressure between the braking surfaces depends upon the material of the brake lining, the coefficient of friction and the maximum rate at which the energy is to be absorbed. The material used for the brake lining should have high coefficient of friction with minimum fading, in other words, the coefficient of friction should remain constant over the entire surface with change in temperature, low wear rate, high heat resistance, high heat dissipation capacity, low coefficient of thermal expansion, adequate mechanical strength, and it should not be affected by moisture and oil. 5. Scientists and scholars are working hard to find the best design to dissipate heat energy rapidly in order to increase the brake performance. Nowadays, there are many literatures which were discussed on the vehicle brake drum design and analysis to improve the performance of brake. Some of these research findings are presented as below. In their study to approve the functionality after modification made on the actual brake drum, Anup Kumar and R. Sabarish, 2014, tested the strength and heat removal ability of brake drum. From the transient temperature test they observed that the temperature is increasing with each cycle. This showed them that the cooling time provided is not sufficient to cool the drum. To get more accurate temperature distributions they determined convection coefficient, H, value by analytical or experimental prediction and incorporated into model. They checked the design by comparing the maximum obtained stress, obtained in analysis against the standard allowable stress value. They found that the design was safe and the brake drum functioned properly under the given load conditions. 6. Durgesh Kaiward and Yogesh Kumar Temhern 2017, studied on the comparison of structural and thermal analysis of disc brake using various materials. They discovered allo-NiCO alloy and titanium alloy are a good material for brake disc from compare to cast iron and structural steel. 7. DVS RBM Subramaniam and L. Sravani concluded that beside general material, aluminum metal matrix, KS1275, can also be used as the material for drum brake because which is economically less cost and less weight ratio gives nearly same stress and deformation value in static analysis and giving good thermal distribution value. 8. The determination of brake temperature is important for the analysis and design brake of a brake system. Excessive temperatures will cause a decrease in brake torque production commonly called brake fade, and may cause increased brake lining wear, brake system failure, and damage to adjacent components such as bearings and tires. 2. 1.2 Objective of the study. The objectives of this study were 1. To design heavy-duty brake drum using CATIA V5. 2. To design heavy-duty brake shoe using CATIA V5. 3. To analyze the structural and thermal characteristics of brake drum using ANSYS 14. 4. To analyze the structural and thermal characteristics of brake shoe using ANSYS 14. 5. To discuss on the result of the design by using various brake materials. 1.3 The purpose of the study. On this research it is aimed to find an alternative brake material for heavy-duty vehicle brake drum and brake shoe by using 4 brake materials as a design variables and comparing their structural and thermal characteristics using the same model and analysis software. 1.4 Significance of the study. The finding of the study would have positive impact on the development of engineering knowledge and skill. It is helpful to develop the design capability using C8 software, CATIA. It is helpful to develop the analysis capability using analysis software, ANSYS. From industrial perspective the findings may bring alternative materials for consideration as brake materials. 1.5 Research problems. The drop in brake performance to control motor vehicle during downhill drive that normally needs continuous application of brake to control the speed of the truck is a challenge for truck drivers. The consequence of failure of brake is dangerous because it has great possibility to bring the car into crash and damage. As the result of crash, the loss of materials and sometimes loss of life could be happen. There are various factors that contribute to the failure of brake to control the truck. Some of them are brake design, technical problem, high vehicle speed, road type, and weather condition. 1. Theoretically, the heat generated during braking is designed to be absorbed by the drum in the process of conduction and the surrounding air in the process of convection. Some amount of heat is dissipated by radiation from the brake system. Poor design and low quality of materials of the truck drum brake are insufficient to handle continuous brake application because of rapid wear and low thermal dissipation, which then increases the drum temperature and causes early fade of brake. This research study is focused on the existing truck drum brake design and materials, heat dissipation capacity, and finding the solutions for improving heat dissipation of brake by using different brake materials. To construct the brake drum and shoe CATIA has been used, and to analyze the brake drum ANSYS software is used. 2. Brake drum design. The design or capacity of a brake depends upon the following factors: 5. The unit pressure between the braking surfaces. The coefficient of friction between the braking surfaces. The peripheral velocity of the brake drum. The projected area of the friction surfaces, and the ability of the brake to dissipate heat equivalent to the energy being absorbed. The brake drum geometry of this study is identified and its parameters are shown under Table 1.9. Table 1. Parameters of brake drum design. Category: Commercial heavy-duty light truck. WL, loaded weight, kg. 30,000. WC, curb weight, kg. 12,290. Vmax, km/h. 75. Brake surface diameter, mm. 420. Overall depth, mm. 241.3. Brake surface flat, mm. 187.45. Bolt circle diameter, mm. 285.75. Pilot diameter, mm. 239.776. Backplate thickness, mm. 14.22. Bolt holes, mm. 10/20.574. 2.1 Brake materials. The four materials chosen for the analyses are carbon steel, Al alloy, Al metal matrix, composite, MMC, and cast iron. Carbon steel and cast iron are commonly used brake materials. Their property is shown under Table 2.2, 5, 6, 7, 10, 11, and 12. 2.3 Design of drum brake. The design of the drum is done using the parameters of brake drum in CATIA. The views are extracted and dimensions were generated for front and top views, and the views of drum are shown under Figure 1. 2.4 Brake shoe design. The design of the brake shoe has been done in CATIA using the parameters of brake shoe. The front, top and isometric views were projected from the designed brake shoe as shown under Figure 2. 3. Analysis using ANSYS 14.5 Workbench introduction. Simple shapes and simple problems can be, and often are done by hand. Most real-world parts and assemblies are far too complex to do accurately, let alone quickly, without use of a computer and appropriate analysis software. Finite method, FEM, has been used as a tool to solve engineering problems commercially in industrial applications. Commercial software have FIA tool, like ANSYS, Abacus, Fluent, and COMSOL Multiphysics EDC. Finite element analysis, FIA, is a mathematical representation of a physical system comprising a part/assembly, model, material properties, and applicable boundary conditions, collectively referred to as pre-processing, the solution of that mathematical representation, solving, and the study of results of that solution post-processing. 4. 3.1 Structural analysis of brake drum. A. Import model. In the pre-processing stage of FEM, the brake drum and shoe geometry were imported from CATIA v5 into ANSYS 14.5 Workbench as shown under Figure 3 and 4 respectively. B. Load and fixed support. To study the structural load characteristics of brake materials, applied load and support were determined. Brake pressure of 1.5 MPa is applied on the face of brake drum and in the brake lining as shown under Fig 5 and 6 respectively. Fig 7 and 8 illustrate fixed support. C. Meshing. The process of representing a physical domain with finite elements is referred to as meshing, and the resulting set of elements is known as the finite element mesh. Meshing of the brake drum is shown under Fig 9. Mesh type, tetrahedral. No of nodes, 41,273. No of elements, 23,051. Structural analysis of carbon steel brake drum. Carbon steel drum brake has showed maximum total deformation, maximum equivalent, von Mises, stress and maximum equivalent elastic strain at the face of the drum highlighted by red color, each have magnitude of 0.020502 mm, 18.783 MPa, and 8.9446 E5 mm/mm respectively. The drum's bolt holes area has lower deformation, stress and strain as indicated by blue color. The detail is shown under Fig 10, 11 and 12. Structural analysis of alloy brake drum. Alloy brake drum has showed maximum total deformation, max equivalent, von Mises, stress and max equivalent elastic strain at the face of the drum as indicated by red color and minimum deformation, min equivalent, von Mises, stress, and min equivalent elastic strain at the bolt holes area of the drum as indicated by blue color. Fig 13, 14 and 15 show the detail of deformation, stress and strain of alloy brake drum. Structural analysis of metal matrices composite brake drum. Metal matrices composite brake drum has showed maximum total deformation of 0.044231 mm, maximum and minimum equivalent, von Mises, stress of 18.64 and 0.087663 MPa respectively and maximum minimum equivalent elastic strain of 0.00019021 mm/mm and 1.0611 mm/mm respectively. Fig 17, 18 and 19 show the deformation, stress and strain of metal matrices composite brake drum. Structural analysis of cast iron brake drum. Cast iron brake drum has showed maximum total deformation of 0.043054 mm, maximum and minimum equivalent, von Mises, stress of 18.783 and 0.077733 MPa respectively and maximum minimum equivalent elastic strain of 0.00018784 mm/mm and 9.0238E7 mm/mm respectively. Fig 20, 21 and 22 show the deformation, stress and strain of cast iron brake drum. 3.2 Structural analysis of brake shoe. Meshing. The element size and type of mesh were defined and the brake shoe has been meshed as shown in Fig 23. The statistics of nodes and elements are: mesh type, tetrahedral. No of nodes, 16,738. No of elements, 8,916. Structural analysis of carbon steel brake shoe. Carbon steel brake shoe has showed maximum total deformation, equivalent, von Mises, stress and equivalent elastic strain of 0.058955 mm, 238.3 MPa, and 0.001134 mm/mm respectively as highlighted by red color and minimum deformation, equivalent, von Mises, stress and min equivalent elastic strain of 0.27163 MPa and 2.5266 E6 mm/mm respectively as indicated by blue color. Fig 24, 25 and 26 shows the deformation, stress and strain of carbon steel brake shoe. Fig 26 strain structural analysis of alloy brake shoe. Alloy brake shoe has showed maximum total deformation of 0.17312 mm, maximum and minimum equivalent, von Mises, stress of 229.68 and 0.28859 MPa respectively and maximum minimum equivalent elastic strain of 0.003235 mm/mm and 7.2523 E6 mm/mm respectively. Fig 27, 28 and 29 show the deformation, stress and strain of alloy brake shoe. Structural analysis of MMC brake shoe. MMC brake shoe has showed maximum total deformation of 0.12542 mm, maximum and minimum equivalent, von Mises, stress of 229.68 and 0.28859 MPa respectively and maximum minimum equivalent elastic strain of 0.002343 mm/mm and 5.2542 E6 mm/mm respectively. Fig 30, 31 and 32 show the deformation, stress and strain of MMC brake shoe. Structural analysis of cast iron brake shoe. Cast iron brake shoe has showed maximum total deformation of 0.1238 mm, maximum and minimum equivalent, von Mises, stress of 238.3 and 0.27163 MPa respectively, and maximum-minimum equivalent elastic strain of 0.002383 mm/mm and 5.3058 E6 mm/mm respectively. Fig 33, 34 and 35 show the deformation, stress and strain of cast iron brake shoe. 3.3 Thermal analysis brake drum and shoe. The temperature applied to study the steady-state thermal analysis of the brake materials is 90 OC, and the convection coefficient is 5E006W/mm2. Fig 36 Fig.39 illustrates the thermal study. Thermal analysis of brake drum. Aluminum alloy brake drum has showed maximum and minimum temperature of 90 OC and 88.519 OC respectively. The maximum and minimum total heat flux of 0.007164 W/mm2 and 6.1651 E6 W/mm2 respectively. Fig 40 and 41 show the temperature and heat flux of aluminum alloy brake drum. Thermal analysis of aluminum metal matrices brake drum. Aluminum MMC brake drum has showed maximum and minimum temperature of 90 OC and 88.458 OC respectively. The maximum and minimum total heat flux of 0.007160 W/mm2 and 6.1593 E6 W/mm2 respectively. Fig 42 and 43 show the temperature and heat flux of aluminum MMC brake drum. Carbon steel brake drum has showed maximum and minimum temperature of 90 OC and 85.591 OC respectively. The maximum and minimum total heat flux of 0.006994 W/mm2 and 5.8853 E6 W/mm2 respectively. Whereas, cast iron brake drum has showed maximum and minimum temperature of 90 OC and 85.591 OC respectively. The maximum and minimum total heat flux of 0.006994 W/mm2 and 5.8853 E6 W/mm2 respectively. Fig 44, Fig.45, Fig 46 and 47 show the temperature and heat flux of carbon steel and cast iron brake drum. Thermal analysis of brake shoe. Aluminum alloy brake shoe has showed maximum and minimum temperature of 90 OC and 88.115 OC respectively. The maximum and minimum total heat flux of 0.012893 W/mm2 and 0.00017892 W/mm2 respectively. Fig 48 and 49 show the temperature and heat flux of aluminum alloy brake shoe. Aluminum metal matrix composite brake shoe showed maximum and minimum temperature of 90 OC and 88.038 OC respectively. The maximum and minimum total heat flux of 0.012883 W/mm2 and 0.00017891 W/mm2 respectively. Fig 50 and 51 show the temperature and heat flux of aluminum alloy brake shoe. Carbon steel brake showed maximum and minimum temperature of 90 OC and 82.451 OC respectively. The maximum and minimum total heat flux of 0.012165 W/mm2 and 0.00017827 W/mm2 respectively. Whereas, cast iron brake shoe showed maximum and minimum temperature of 90 OC and 84.127 OC respectively. The maximum and minimum total heat flux of 0.012382 W/mm2 and 0.00017841 W/mm2 respectively. Fig 52, Fig 53, Fig 54 and 55 show the temperature and heat flux of carbon steel and cast iron brake shoe. The structural analysis result of the brake shoes seen in Fig 23 to Fig 35 depicts that Al alloy had higher deformation than the three materials, whereas, Al metal matrix composite and cast iron have very similar deformation characteristics and carbon steel showed lower deformation property. In the stress analysis of brake shoe, carbon steel and cast iron have slightly higher stress than Al alloy and Al metal matrix composite. Al alloy showed higher strain than the three engineering materials, whereas Al metal matrix composite and cast iron exhibited similar strain characteristics. while carbon steel have lower strain. The summary of stress, strain, and deformation of the brake shoes is shown under Table 4. The steady-state thermal analysis result that has been seen under Fig 36 to Fig. 47 computed for brake drum between 4 engineering materials by applying 90 OC and convection coefficient of 5E006W/mm2 showed alloy have higher temperature distribution characteristics than cast iron and carbon steel. It has small variation with metal matrix composite. Alloy and MMC have slightly higher heat flux than carbon steel and cast iron. The summary of temperature and heat flux of the 4 materials are shown under Table 5. Similarly, in the steady-state thermal analysis result of brake shoe that have been seen under Fig 48 to Fig 55, alloy and MMC showed higher temperature distribution capacity and heat flux while cast iron had higher thermal conductivity and heat flux than carbon steel. The temperature and heat flux of the brake shoe are shown under Table 6. Table 5. The result obtained on this research supports the works of DVS RBM Subramaniam and L. Sravani, 2017. In their study on design and analysis of drum brake using carbon steel, alloy and MMC as brake materials, they concluded that MMC, KS1275, can be used as material for drum brake beside general materials. It also supports the study carried out by Durgesh Kaiward and Yogesh Kumar Temhern, 2017, on the comparison of structural and thermal analysis of disc brake using various materials. They discovered NiCO alloy and titanium alloy are a good material for brake disc from compared to cast iron and structural steel. 5. Conclusions. By integrating CATIA and ANSYS, it is possible to study material effect on the design and analysis of brake performance of heavy-duty truck. Engineering materials have significant effect on the design of a product. Aluminum metal matrix composite, ALMMC F3D205T5, has better characteristics of thermal dissipation capacity and lightweight than cast iron and carbon steel, commonly used brake materials, and it have moderate deformation characteristics similar to cast iron. The brake drum and shoe design requirements regarding heat dissipation and weight has been met. Because of its better characteristics, aluminum metal matrix composite, ALMMC F3D205T5, can be used as an alternative brake material to build brake drums and shoe. 6. Acknowledgement. The researcher would like to appreciate research advisor Professor Zhang for her unreserved support and valuable comments and suggestions on this study.